Hey, what's up everyone? Welcome back to Singularity. We will dive deep into the wildest mysteries of the cosmos and beyond. What is inside Event Horizon? Buckle up because we're about to explore the universe at its most extreme. Let's get into it. Imagine a singularity. What's inside it? Well, a singularity is like the ultimate cosmic enigma. It's this point where our understanding of physics just collapses. You've probably heard of it in the context of black holes, where gravity becomes so intense that space and time get squeezed into this infinitesimally tiny, infinitely dense spot. What's inside? Honestly, we don't really know. Our math breaks down there. It's not like we can peek inside and see a glowing core or some secret treasure. The laws of physics as we know them, like general relativity, tell us that everything gets crushed into this zero-volume point with infinite density. Infinite density. That's wild, right? It's like taking the entire universe and stuffing it into a pinprick so small it doesn't even have a size. But here's the kicker. Because it's so extreme, we suspect there's more to the story, something beyond our current grasp. Now let's shift gears a bit and talk about the inner core of a neutron star. A neutron star is what's left after a massive star goes supernova and its core collapses under gravity. The outer layers blast off, but the core, it gets squished into this ultra-dense ball about 20 kilometers across. Think the size of a city, but weighing more than our sun. The inner core of a neutron star is a whole other level of bizarre. On the surface, you've got neutrons packed so tight they're basically shoulder to shoulder. But as you go deeper, things get even weirder. How dense is it? Picture this. A teaspoon of neutron star material weighs about 1 billion tons. 1 billion tons! That's like taking Mount Everest, shrinking it down to a sugar cube, and then making it 1,000,000 times heavier. Scientists think the inner core might not even be just neutrons anymore. It could be this exotic soup called a quark-gluon plasma. What's that? Well, normally protons and neutrons are made of smaller building blocks called quarks, held together by gluons, like cosmic glue. But in the insane pressure of a neutron star's core, those neutrons might break apart, freeing the quarks and gluons to mix into this wild, super dense stew. It's not a solid, not a liquid, it's this freaky state of matter we don't see anywhere else. Back to singularities for a sec. Do they break quantum theory? Kind of. Yeah. Quantum mechanics deals with the super tiny particles, probabilities, all that jazz. But singularities? They're where gravity goes infinite, and quantum mechanics doesn't play nice with infinity. General relativity says singularities are real, but quantum theory says, hold up, infinite density in zero space. That doesn't compute. So, at the singularity, the two big pillars of physics, relativity and quantum mechanics, clash hard. We need a theory of quantum gravity to fix this, but we don't have one yet. It's like trying to mix oil and water. They just don't blend with what we know now. Enter the Planck star theory, a cool idea to dodge this mess. Some physicists say, what if there's no singularity? Instead, inside a black hole, matter gets compressed down to the Planck scale, the tiniest length possible, about 10 to the power of minus 35 meters. That's a decimal point followed by 34 zeros and a 1, unimaginably small but not zero. At this point, quantum effects kick in, halting the collapse. You get a Planck star super dense but not infinitely so. How dense? Think of it as the ultimate limit of squishing stuff before physics says, nope, no further. It's denser than a neutron star by a ridiculous amount. A neutron star's density is about 10 to the power of 17 kilograms per cubic meter. A Planck star, try 10 to the power of 96 kilograms per cubic meter. To compare that easily, if a neutron star is like packing a mountain into a teaspoon, a Planck star is like packing the entire observable universe into that same teaspoon. And then some. It's a density so extreme, it's almost philosophical. Now, what's this quantum bounce thing? The Planck star idea ties into something called a quantum bounce. Instead of a singularity crushing everything forever, the collapse hits this Planck limit, and quantum mechanics causes it to bounce back. Imagine dropping a ball. It falls, hits the ground, and springs up. In a black hole, matter collapses. hits this Planck star phase, and boom, starts expanding again. Some say this could even spit out a white hole on the other side. What's a white hole? It's like a black hole's opposite. Instead of sucking everything in, it blasts everything out. Think of it as a cosmic volcano, spewing light and matter. Does it exist? We've never seen one, but it's a neat theoretical flip. The quantum bounce and white hole idea suggest black holes might not be eternal tombs. They could be gateways or rebirth points. Why does all this matter? Well, it's about understanding the universe at its extremes. How it begins, how it ends, what's possible. Singularities challenge everything we know, and solving them could unlock the secrets of quantum gravity, the Big Bang, maybe even time itself. Neutron stars and their cores? They're like natural labs for studying matter under conditions we can't replicate. And theories like Planck stars or white holes, they push us to rethink reality. Maybe the universe isn't just a one-way crush, but a cycle of collapse and renewal. The challenge? Oh, it's massive. We can't see inside a black hole or a neutron star's core. Our telescopes spot their effects, like X-rays from neutron stars or gravitational waves from black holes. But the insides? Pure guesswork, backed by math and imagination. Experiments are tough. Recreating these densities on Earth is impossible with current ET. Plus, marrying quantum mechanics and gravity into one theory? Decades of geniuses have tried and hit walls. It's like solving a puzzle with half the pieces missing in the dark with gloves on. But that's what makes it exciting. Every step forward cracks open a new mystery. So there you have it, a whirlwind tour of singularities, neutron star cores, quark-gluon mixes, Planck stars, quantum bounces, and white holes. The universe is wild, dense, and full of secrets. What do you think? Ready to dive deeper into this cosmic rabbit hole? If you enjoyed this journey through the extremes of reality, don't forget to smash that like button. It really helps us out. We've got more cosmic adventures coming your way. See you in the next one.